This video is going over the experiments that led to the discovery of the parts of an atom, the atomic structure. So just a quick review about the structure of the atom. We have two areas to an atom. You have the nucleus and you have the electrons that orbit around the nucleus. The nucleus, of course, is made of protons, which are positively charged, neutrons, which have a neutral charge, and the electrons around are negatively charged. The first part of the atom to be discovered was the electron. And what you see here is what's called a cathode ray tube. These are called the cathode ray tube experiments. So what they do is they pass electric current, because you can see the wires on either side of that glass tube there. You pass electric current through a gas at low pressure. And you see this beam of light, which is shooting across from one end to the other end. That's called the cathode ray. And what you see specifically here is when you take the negative pole of a magnet and you put it near this cathode ray, it is deflected by the negative end of the magnet. So there's going to be a couple of inferences that we can make from this experiment. So here is how the experiment was set up. You have a gas at low pressure. And so they saw that the cathode ray would be created at the cathode, which is the negative end, and it would move towards the anode. And I want to actually go back here and show you how that looks, because here's an actual cathode ray. You can see here there's the metal plates for either the cathode, or in that case, it's the cathode. You have the anode at the other end. And I think the gas inside there is hydrogen, because you'll see it is nice and pink. And so here you can see that's where the cathode ray is moving from the cathode end to the anode end. Yeah, okay. So scientists saw this beam of light basically being created, and they hypothesized that it was being caused by a stream of particles. They called that the cathode ray. And again, it traveled from the cathode, which is negative, to the anode, which is positive. And again, when you have a magnetic field deflecting the ray away from the negative charge of the magnet, that gives you two hypotheses. So the particles that compose the cathode rays are negatively charged. And in J.J. Thomson and the Millikan experiment, they actually determine the ratio of the charge of the electron to the mass of the electron. Those are also important experiments. So we go from the cathode ray experiments, knowing that, if I go back to here, so based on the experiments, of course, what they did was they actually changed out the gas. So they tried different gases, and they also tried changing out the kind of metal that the cathode and anode were made out of. And every single time, whatever variation that they used, whatever metal there was or whatever gas there was, it was always exactly the same result. And that tells us something very important. And that is that all elements are going to have the same type of particle, because the results are the same every time. Even if you change the gas, same result. You change the metal for the electrodes, same result. So that means that all atoms of all elements have this particular particle in them. So we go to J.J. Thomson. J.J. Thomson was able to measure the ratio of charge to the cathode ray particles to their mass. And like I said, it was always the same regardless of the metal or the gas inside the cathode ray tube. So he concluded that all cathode rays are made of identical negatively charged particles, which were later named electrons. So we've now confirmed that the electron carries a negative electric charge, and there's two important inferences that we can also take from this, which is one, where is it? One, because atoms are electrically neutral as a whole, but they're made of negatively charged particles, that must mean that there's another particle that has an equal positive charge. Because you can't, like, if we identify electrons as being negatively charged and electrons are particles within an atom, then that means that there's other particles within an atom that have a positive charge, because atoms overall are neutral. The second observation or inference that we can make based on the observations that we looked at is that because electrons have very little mass, atoms have to have something else in them that makes up most of that mass. The only thing you really have to know about the Millikan's oil drop experiment is that it determined the mass of an electron. It's kind of complicated. Basically, they take an atomizer, which you can see here, and it basically it doesn't actually separate all the atoms, but it turns the oil into extremely small little droplets. And you can see these are magnetic plates here. And because of three different forces, we have gravitational forces, they just fall because of gravity. You also have electrostatic force because there are magnetic plates on the top and the bottom, and something called viscous drag force. Viscosity is the thickness of a liquid. So basically, like, if you have a thick liquid, it will fall. No, it won't fall the same. I don't know. Anyway, like I said, it's complicated, and then they ionized it using X-rays, and somehow they were able to use like a bunch of math. Yeah, see, they're using a bunch of math, and they determined the mass of an electron. So the bottom line is the mass of an electron is 9 times 10 to the minus 31 kilograms. So it's basically almost insignificant. So again, this supports the fact that there's other particles in an atom that make up the mass of the atom, and there has to be something in there that has a positive charge to balance out the negative charge of the electron. Okay, so from these experiments, we have a model of the structure of an atom, which we call the plum pudding model, based on an English dessert called plum pudding. You can also think of it like a watermelon, where you've got these negatively charged seeds inside of a positively charged atom. And he's just talking about plum pudding. Okay, so that's the discovery of the electron. Next, we go to the discovery of the nucleus, which was the second part of the atom to be discovered. It wasn't the proton and neutron specifically, but the nucleus as a whole. This also happens to be my personal favorite experiment of all time because of the results and what Rutherford ended up saying about the results. And I really, really love that quote, which I have in here. So this is about 14 years after J.J. Thomson. He was in 1897. This is 1911. Ernest Rutherford was a New Zealander, and he had help from his associates. The experiment entails taking a thin gold foil, and you're going to bombard or shoot it with an alpha particle gun or laser, or I don't know what you would call it, an alpha, yeah, something that shoots out alpha particles. What is an alpha particle? An alpha particle is the nucleus of a helium atom, and the nucleus of a helium atom is comprised of 2 protons and 2 neutrons. So compared to hydrogen, which has only 1 proton, it is 4 times the mass of a hydrogen atom, and it has a positive charge because you have no electrons, because it's just the nucleus of a helium atom. So because of the plum pudding model from J.J. Thomson, we were assuming, not we, but they were assuming that the mass and the charge of an atom was uniformly distributed throughout the atoms of the gold foil. You have this kind of random distribution or spreading out of negative and positive charges. So they expected that the alpha particles would pass straight through with only a little bit of deflection because you have this really even distribution of charge. What really happened is that most of the particles kind of did what they thought. There was like, they passed through, you can see based on the animation, passed through with only slight deflection. However, 1 out of every 8,000 alpha particles had a wide deflection rate, which you can see here. This is a screen that recorded. So if you see the little yellow pings there. You see it there, and sometimes you see it over here. That's a huge deflection. It didn't go straight through, but some of them, 1 out of every 8,000, hit the gold foil and were like almost bounced back. And this is one of my favorite quotes. Rutherford explained it as, quote, as if you had fired a 15-inch artillery shell at a piece of tissue paper and it came back and hit you. What that means is basically if you have a 15-inch, like this big bullet, right? Artillery shell is a bullet. And you shoot it at a piece of tissue paper and the bullet doesn't go straight through, it hits and gets bounced back. That is an amazing quote. So here in a diagram, what they expected, you see only a very slight deflection, but most of it's going straight through. What really happened is that you had a very wide angle of deflection, and you even have some being almost completely bounced back, which was very, very unexpected. So how do we explain these results? Rutherford thought about this for 2 years. Can you imagine doing an experiment and not having an explanation for these crazy results you got for 2 years? Like, I think nowadays most people would just like give up. They're like, I don't know. Like, I don't know. But he finally came up with an explanation. The rebounded alpha particles must have experienced some powerful force within the atom. He called that the nucleus. And so because it basically rivaled the mass of the alpha particles, so it has to be big compared to, you know, electrons that we've discovered already. But it also has to have a positive charge because the alpha particles have a positive charge, and these alpha particles that like hit something and were completely deflected back, that must mean that it has a positive charge. So this is the discovery of the nucleus, because the alpha particles are hitting something that must mean that it has some significant mass, and it must be positively charged in order to deflect the alpha particles so greatly. So here is a demonstration of the experiment, and you can see just how wide the angles were from these alpha particles that are being deflected by something in the gold foil. They really expected it to just go straight through, but you see how wide the angles are. So looking at it at a molecular level, what's actually happening here? So what you see is the nucleus. You see a lot of the alpha particles would go straight through, but you have a lot of deflection because they're hitting something that has a significant mass and a positive charge. Okay, so that is the gold foil experiment. So because you had 7,999 alpha particles actually passing through, that means that whatever they're hitting is a very small volume, because like I said, only 1 out of every 8,000 particles is actually hitting something and deflecting back, which means most of it's empty space. So if the nucleus were the size of a marble, the size of the atom would be about the size of a football field. So it turns out that an atom is actually mostly empty space. But where were the electrons? So Rutherford discovered something very small that has significant mass and positive charge, but where are the electrons? Rutherford suggested the electrons surrounded the positively charged nucleus like planets around the sun, but he could not explain what kept the electrons in motion around the nucleus. Like, why not just fly off? So here is the model of Rutherford's atom, which you have a dense nucleus, which has positive particles in it, and negative electrons that orbit around it. Except for hydrogen, all atomic nuclei have 2 kinds of particles. Proton is positive, neutron is neutral, electrons are negative. So because atoms are electrically neutral, the number of protons and electrons is always the same for an atom. Things get different when you start talking about ions. The nuclei of atoms in different elements are different in the number of protons they contain, and therefore in the amount of positive charge they possess. So the number of protons in an atom's nucleus determines the atom's identity, what type of element it is. So one of the last things to consider about the atom is we know that protons and neutrons are in the nucleus. We know that the nucleus contains the majority of the mass of an atom, and it occupies a very, very small volume. And we also know that particles that have the same electric charge usually repel one another. So what is keeping the nucleus together? If it's made of only positive and neutral particles, why wouldn't those positive protons repel each other? So you would expect a nucleus that contains more than one proton to be unstable. But it turns out that when two protons are really close together, they actually have a strong attraction for each other. And these are called nuclear forces. They're short range proton-neutron, proton-proton, and neutron-neutron forces that hold the particles together.